Hi there, this is session 30 of programming from the very basics using Python. In this session, we will learn about generators and how to use them to build concurrent code in Python. Well, to understand what generators are, I will show you some simple examples and highlight certain problems in those programs, and I'll tell you how you can solve them using generators as such. So let's take a simple example which I've already typed it out over here to save time. So I have a function to generate Fibonacci series, which you can see here. And I think this program might be familiar to you. In my earlier sessions, I did write a program this way to demonstrate the use of parallel assignment and about loops. When I talked about the for loop, I think I told you this example. So when I type fib of 10 as an argument here, this 10 is passed as an argument n to this fib function. And as you can see here, I'm initializing two variables, the local variables inside the fib function, which is a and b, whose values are 0 and 1. And now you can see that I'm using a for loop. Just because I'm not really interested in the variable, I'm using an underscore here because I'm not going to use this variable inside this loop. So if I'd used it as I or v or any other labels, it's just inferring that I might be using them in a loop. To indicate that there's a don't care variable, I'm using an underscore here as a placeholder in range of n, which means that this for loop is supposed to execute this body n number of times. So if I pass 10 here, this body will execute 10 times. Now in this particular loop, you can see that I'm printing the value a followed by a space. That's the end separator, followed by a becoming b and b becoming a plus b. I think I explained how this works, and the final outcome of this is a Fibonacci series that you see here, which starts off with 0 and 1. We can see that a is 0, then it prints that value 0, and a becomes 1, which is the value of b, and b becomes a plus b, that is 0 plus 1. And the next iteration, you can see that a is printed based on the value that got assigned in here, which is 1, followed by again rerunning this statement, which means a becomes 1 more time, but b becomes 1 plus 1, that is the current value of a plus the value of b, which is 2. And then again it prints 1 that you see here, followed by, you can see a becoming b, which is 2 this time, and b becoming 1 plus 2, which is 3. And this cycle repeats until 10 numbers in the Fibonacci series are printed. Now, what's the problem with this, you might ask? This code works, and it's very Pythonic, you might say. From the design, you can see that this particular function is not really usable. Why do I say that? This function prints the Fibonacci numbers on the screen because I'm using the print function here. But maybe what I want to do is I want to get those Fibonacci numbers and maybe find out the sum of it. I want to find out the sum of all first 10 Fibonacci numbers, or maybe print those Fibonacci numbers with their squares. Or maybe I want to find out which of those Fibonacci numbers are prime numbers, or get all the odd numbers from a Fibonacci sequence. There are a lot of use cases, right? So you have a function that is generating values, and you want to get those values and perform further computation on that. And that is not achievable with this particular design because this function directly prints it on the output and I cannot get it in my program. So if I want to make this more usable, then one of the ways I can solve this is by implementing another variant of this, that is using a list. Maybe the fib function, rather than printing these numbers on standard output, if you could accumulate it into a list and return a list, maybe I can use it. Now let's try that out. So if you're one of the ways I can do that is I can create a series as a list, which starts off as 0 and 1. By the way, this example you will find in the Python tutorial, by the way. If you look at the Python tutorial documents from the official Python docs, you'll find both of these examples there in the tutorial. I'm just trying to show you this, right? So in this case, the series is initialized as a list with the initial values 0 and 1. And now I need to generate maybe n minus 2 more. For example, if I say 10, if n is 10, there are two values already in the list. I need to generate 8 more numbers and accumulate it into a list. So what I'm going to do here is I'm going to type for underscore in range of n minus 2, and then here, instead of printing the values, or I'll remove even this line, you don't need this because there's no A and B anymore. What I need to do is I need to append to the series. And now you might wonder, what do I append? Think, how do you complete this? What will you do to complete it? And yes, the final step is to return series. But this is where the real magic happens. Now, can you just pause for a moment and think, what would you do in this append method? Well, think about it. I have 0 and 1 as two items in a list. How do I generate the next one? I will take 1 and 0, add them, and then append them into the list. So what I'm effectively doing is taking the last two items of the list. Currently, the last two items are 0 and 1. They're the only two items in the list right now. So I take the last item, the last but one item, take it out, add them up, append them back into the list. How to generate the next number? Take the last two items again, add them up, append it back to the list. You see where I'm getting? So how do you formulate that particular expression here? Well, how do you get the last item of a list? You can just type series of -1 here. That'll get you the last item of a list. How do you get the last but one item? Previous to last item. So you can do that by using plus series of -2. This is elegant, in my opinion. So now when I run this code, what you can really see is that this fib function, rather than printing anything on the screen, on the standard output, it returns a list, which also means I can capture this in a variable, and then I can use that. I can maybe take for value in R, I can maybe type print R and maybe print the square of R perhaps by multiplying them. So any kind of post-processing can be done. Oh, there is some error. What is the error here? Okay. Oh, okay. There's written a list, isn't it? Oh, I used R here. See here. Just quickly typed it out. So it's obviously a mistake. So you can just type V here and type V into V. You know what I'm trying to do here? I try to multiply a list. Obviously, it's a mistake. It's a typo, right? So when you use simple single letter variables, this can happen. So yeah. So I'm just trying to say for V in R, which is nothing but a list that the fib function returned, iterating over that R, printing V and V into V, and now we can see the outcome. Now this function is quite reusable because rather than printing the Fibonacci numbers on the screen, which was done by the previous function, this function returns it as a list, which I can process it later on by my code. So which I did here. Maybe I can find out the sum of them. I can iterate over them and find out which are all the odd numbers in this series, or maybe find out if there are any prime numbers in it. So all this kind of post-processing or any other extra computation can be done based on the result or based on the outcome of the fib function. Now, this particular function looks good, but there's a problem with this. Until the fib function returns the entire list, I cannot do any processing further. These are two issues. Issue 1, you're returning a list. Now, this list can take up more memory if rather give a larger value. For example, if I try to say fib of 1000, this will generate first 1000 Fibonacci series, which is, the 1000 Fibonacci number will be very big, very, very big because you're doing consecutive adding. You can see that the 10th Fibonacci number is already quite a large number. Not a large number in this case is 34, but the moment you make it 100, it becomes very big. I can show you right here. Look at the 100 Fibonacci number. It's quite large, right? Imagine doing 1000, the number becomes bigger. Plus there's a list. You have a list of those numbers that must be created first, then handed over to the caller, and the caller is going to process it. That's one issue, which takes up more memory because you're returning a list when you're returning very large values. Think about numbers to the extent of million, right? Now, the practical scenario for this is, imagine I'm opening a file, and which I will do talk about in the next further sessions. When I do file IO, you'll see generator patterns being used there. It's possible that I have a text file which has got about 10 lines. I can open the text file and read the text file and process 10 lines, right? One way to do that is I can read the entire file into memory. 10 lines, I think it's readable into memory. Modern computers have enough memory. But what if a file is a log file which is having about 20 million lines? Maybe you don't have that amount of memory. Possible. If you run in a container or any constrained environment, you might not be given that amount of memory for your program. Your program memory could be restricted. So reading 10 million lines into RAM and then processing line by line can be quite expensive, because that's the kind of pattern I'm talking about here. So you have a function that returns a list of values. Processing them will be time consuming, because first you need to create that list. The function has to accumulate the list and hand it over to the caller. That takes up memory and you have to process it. And after that, you don't need it after that, right? So this is one problem. The second problem is more inherent. This code is not concurrent. What I mean by saying that is that until this function hands over the entire list to me, I cannot do any processing. This is called as sequential execution. Think about it this way. You have a worker, maybe your friend, or may not be a worker. It can be anyone. Like you're just interacting with somebody, maybe your teammate, let's say. And you ask your teammate to do some task, process a couple of things, right? Now, one way to do that is you tell him the instructions, him or her the instructions, and wait until the entire task is done. Or two, as and when the task is completed step by step, you want to process the outcome of it. That's what you do. Think about it in a typical scenario you can think of is, let's say, a hotel where you have a lot of chefs working together. Or there's one chef who's preparing some dish, and the other chef wants to serve them. May not be serving. Maybe there's a server in the restaurant who's going to serve what is being prepared. Maybe you went to that restaurant and you ordered, you looked up the menu and you ordered a couple of things from your food. You look up the food menu, you ordered some snacks or maybe the appetizer, let's say, and then you ordered some main course. Maybe before the main course, you ordered some soup, let's assume, and then you ordered the main course, and then you want to order a salad. One way of serving it is all these orders. Maybe you ordered about 4 different items, right? And maybe an appetizer, a soup, a main course, and a salad. You order them, you place it out to the server or the waiter, and the waiter goes to the chef and gives that order. One way is you're made to wait until all of the dishes are done by the chef, and then in one big platter, it is served to you. So you have the appetizer, you have the soup, you have the main course, and you have the salad. All of them at one go. But it could be a long wait because each of these dishes take time. Maybe creating the appetizer, cooking the appetizer or whatever, making it or whatever, right? Creating the appetizer will take about 5 minutes, and a soup takes about 20 minutes, and the main course could take about another 15 minutes, and maybe the salad would take about another 10 minutes. So all these are added. 5 minutes plus 10 minutes plus 20 minutes plus 15 minutes are added. That's the kind of time, right? So that's a total time taken for the entire menu that you have placed. And maybe about after that long time, that of wait, you're served with the entire plate. But we customers, when we walk into restaurants, we are always hungry and we want something to eat while the other thing is happening. So normally when you go and place an order in the menu, most of the restaurants, the dining restaurants that is, they are smart. They make the entire task concurrent. To the chef, the order is given by the waiter. And the chef now first prepares the appetizer, which finishes in about, let's say, 5 minutes or 10 minutes, whatever the time is. And you have to wait for 10 minutes, that's it. And then the appetizer is given to you. And while you're munching on that, the chef is now preparing the soup. And by the time you're done with the appetizer, the soup arrives. keeping you busy. Now you're busy with the soup. By the time you finish the soup, your main course arrives. And by the time you're munching the main course, the chef can relax and then make a salad for you. And the salad is ready by the time you finish your main course. Which one do you prefer? Well, you didn't have to wait for almost like 30 or 40 minutes straight to get your entire dish. You waited for just 10 minutes. And now when you're eating, when you're munching on the appetizer, concurrently the soup is being prepared. And by the time you finish the appetizer, maybe the soup is served. And by the time you finish the soup, the main course is ready. And by the time you finish the main course, the salad is ready. This is an act of concurrency. This is what we mean by concurrency in the real world. The same way in programming, if you want to make this code concurrent, first I'll show you the issue with the non-concurrency here. Generating a Fibonacci numbers are quite fast by modern computers. It's just a question of just adding two numbers and adding them into a list. Now, assume this computer is the ancient computer, and somehow you got Python working on that very old ancient computer of the 1970s or 60s, perhaps. Even they could be quite fast at this, by the way. And maybe the Python runtime is slow on that. Let's assume that. And generating each Fibonacci numbers, let's assume it's going to have a delay of 1 second. So how much time it will take to prepare the list? Maybe about 8 seconds in this case, because n minus 2, right? Maybe if I just make it 10 here, right? If I just say generate the first 10 Fibonacci numbers, it's going to take about 8 seconds. Let me just simulate that. One way to simulate that is by using the time module. So I'm going to use import time. And here, after appending to this list, I'm going to put a sleep here. Sleep of 1 second. Oh, I should call it time.sleep, by the way, because I said import time. So sleep is a function in time module. So what does sleep do, you might ask me? Let me just create a cell above. Hang on a minute. Where did it go? Where did it go? Oops. Okay, this cell got compressed. Hang on one moment, please. Okay. The IDE feature. All right. So here I create a cell above by using A. I'm in command mode. And the moment I type import time, and I'll say hello, and put a sleep of 2 seconds, and then print world. Oh, you can see what's a mistake here, right? I used import time, but I called sleep directly. So you should call it as time.sleep. Now, this is one use case where, sleep is a function that's only available from the time module largely. So it's, I would rather say from time import sleep as a more apt way. I can say from time import sleep, because sleep function is not so generic. It's generally available only in the time module. So you can actually use sleep like this here. There's 2 second delay at which it prints world. Or maybe if at all you want to print some dots like some kind of a progress, just see this. But it's for underscore in range of 10. And if I try to print a dot, and end is equal to empty string here. If I run this now, the 10 dot just come up as is. But if I print this dot and then put a sleep of 1, you can see, you can observe what's happening at the output here. The dots are printed with a 1 second delay. This entire loop takes about 10 seconds to complete, right? So just trying to show you what the role of sleep function is, right? It puts a delay. It just makes the CPU block. It blocks the CPU. When I say blocks the CPU, it blocks the program, rather, not the CPU. It blocks the program from execution for the time. Then it wakes up the program and then tries to execute it. It's like you're putting a pause on the program. You're pausing the program for this much time. Basically, sleep can take time in seconds. You can also make it milliseconds by passing floating point. But there are also variants in the time module to sleep at millisecond, microseconds, or even nanosecond level. So you have different functions for that. I think this should be very basic use case for us. So I'll talk about all the other functions in time module when I talk about standard library modules in another session. So here I'm using the sleep here. So this time I use import time. So I'm using time.sleep of 1. So there's going to be a 1 second delay for every number being appended into the series. Now when I run this, you can see that there is no output up to 8 seconds. You can see the time is ticking there. It's after 8 seconds, you see the entire output coming up. It's like the waiter made you wait for a long time and then serve all the dishes in one go, right? So you see all the dishes in one go, maybe after about a long delay. And that's exactly happened here. If you want to make this concurrent, you need to transform that function into what we know as a generator. And you might ask me, how do you do that? Here's an example. But before I even talk about that, there's another way to implement concurrency, by the way. Another way to do it. First, I'll talk about that. And then I'll come to how do you do it the Pythonic way. If you want to make this code concurrent, this function concurrent, one of the way is to transform this into some kind of a higher order function. I talked about higher order function in the last session, right? So I can use that to also solve concurrency problems. I'm going to show you how it is done. I'm not going to generate a list. I'm not going to create a list anymore. I'm going to go to the old school technique where I was using this logic. I'm going to copy this. Right. Now, as you see, the problem with this code is that, yes, I want to keep generating Fibonacci numbers. That's fine. But what do I do with it? I'm printing it here. But maybe what I want to do with the Fibonacci numbers must be decided by the caller. The caller has to decide what's to be done with the Fibonacci numbers, right? And that's where we replace the print function with a callback. So we replace this print function and we call this callback of pass the argument. And what is this callback? I'm going to take this as one of the parameters in here. And what is this parameter called callback? That's a function that I'm supposed to pass. So here, what I will do is displays. I'm just going to take this fib of 10, right? I'm going to replace that. Okay, not this way. Hang on a minute. Here I can just type fib of 10 and I can just use a callback as callback takes an argument a. So I'm going to use lambda x colon. I can just use print of. I can just provide x comma x into x. So I'm creating a function using lambda expression. And then I'm trying to say that given an argument which the fib function throws at it, you want to print it along with the squares, which we did earlier with the for loop, right? I can do the same thing here. Let me try to run this. You get the same outcome. In fact, if I use a delay here, you can very well see that as and when the numbers are generated, my function is called. This is another way to implement concurrency. Implementing concurrency or concurrent code, or I can say concurrency, using higher order functions with callbacks. We can call this event callbacks. It's just a pattern and is found quite commonly used in a lot of functional programming languages. A lot of concurrent functional programming languages support this kind of a feature and they sort of encourage it. So what we really do here is that we define a function which takes in a parameter and takes another parameter which is supposed to be a callable object, which is in this case a function, right? And here, same thing, a comma b is 0 comma 1 for underscore in range of n, that means n number of times. Just call this function passing a as an argument. But look at the function call here. What am I doing here? I'm creating a lambda expression. So what I pass in as hey here will come up as x to this function because this creates a function object that takes in a parameter. I just created a function. I'm passing it as an argument. If you're still clueless about lambda expressions, go back and visit my previous video in the session where I talked about lambda, higher order functions and lambda expressions. Have a look into it, look into it and experiment with it so you get some good understanding. If you still have questions, still find confusion, do post it on comments. I will explain it. So here, I created a function, defined a function, which should take an argument. And when this function is invoked with that argument, what it's supposed to do, basically an expression. Oh, I'm using print here, which does not return anything, but I'm not taking any return value in this. If you observe, this callback is not, I'm not taking any return value of the callback. No, just calling it, right? Just then in such case, you can use a expression, which can be a function that returns nothing. In this case, which will take x as an argument and then x into x. So it'll print the number and it's squared. So whatever you want to do with that value being generated, that is determined by this expression here. Maybe you want to square it. Maybe you want to find out if it's an even number, print if it's an even number. So all this can be done. Maybe you can also do this. You can, rather than printing all the numbers with their squares, I want to print the even numbers of the first 10 Fibonacci series. And if I want to do that, I can just type fib of 10, comma, lambda x colon print of x, but I have to make it an expression. So I'd say if maybe x percentage 2 equals 0 or none. Yeah, it's a small problem here. Okay, else none. Sorry, else none. Let's try this. You can see only numbers which are even are printed. There are delays, right? There are delays. There are twofold advantages with this. One, you're not constructing a list and handing over to the caller. You're expecting the caller to provide his callback, and that you will invoke in this higher order function when you are able to generate a number. That's why we call this event callback. The event is you generated a new value of A. The moment you generate a new value of A, you're calling this function that is handed over as an argument. You'll see this kind of patterns used in a lot of these front-end technologies like JavaScript. I've seen a lot of JavaScript code there. They use a lot of these callback features. The problem with callback is for simple use cases, fine, but sometimes your callback can take a callback as an argument. And that callback can take another callback as an argument. Maybe your callback also is another one more layer higher order function, which wants to do some processing and then do something else, which could be another function. And this kind of a design can be sometimes termed as the callback hell. So you have one callback, which is going to invoke another callback, which is going to invoke another callback, and your code becomes completely complicated to understand. The flow control is quite complicated. Python provides another technique to solve this though. I'm going to show you that. And that is exactly where I'm introducing generators. First, I'm going to show you how it is done. Then I'm going to explain what really happens under the hood. So how I solve this in Python, I'll just use import time again. This time I'm going to diff fib, right, of n. And here, I'm going to start off with the same thing, 0, 1 for underscore in range of n. And I can just try. Earlier I was using print a and n is equal to space. Let that be, let that be, let that be. I want to modify that. And a comma b equals b comma a plus b. And the main program, what I did was, I could say r is equal to fib of 10 this time. And then I could say for, value in r, I could just print v comma v into v. It's a mixture of two code, right? The code implemented is the first one. But here, right, the function definition is like the first cell which I showed you. It's the same. But this code is from the second cell where I'm expecting a list and I'm iterating over a list. But that doesn't work, right? If I try running this, it's going to throw, you can see that this fib function prints all the Fibonacci numbers. It returns nothing. You cannot do any post-processing here because it's failing. You can see that right here. This for loop, none type object is not iterable. Now I'm going to make some change. All I do is remove this print from here. And instead, I'm going to use a new keyword, new statement I'm introducing you to. It's called yield. I say yield A. The moment I use the yield statement here and say yield and a value, just see what happens. This works like magic. I'm going to put some delay here. That's the real fun. I'm going to put time.sleep of 1. And I guess I didn't import time. Yes, I did. I'm going to run this code now. There's a cell. There's a complete cell that you can see, right? So what it is. If you look at this code, it's exactly similar to the code that I showed you first. I just added a sleep for a delay for generating every Fibonacci numbers. And then instead of print, I'm using yield, right? And then here, I'm trying to get the return value of fib. Looks like fib is returning nothing here. So return value should be none, right? But just observe what happened. This works. You don't have to pass a callback to fib and figure out. So you don't have to build an higher order function. This is more imperative style and it still works, right? And it's also concurrent. No list is created. So you might wonder, what is this fib returning? Now I'm going to dissect it down and explain what really happens the moment you use yield inside a function. Let's create a very basic function this time. That's a def, test def. We'll just call it test function, right? And I'm just going to start off with start of testfn code. The code inside testfn. I'm just printing a message here by using print. After which I'm just going to put a return 100. If I put anything after return, does it make sense? Continuing in testfn code. You can see that that particular line is sort of dulled down by the IDE to prove to you, to tell you that, to hint you that this is an unreachable code. Why? Because when you call testfn, this function executes the moment you call it. That means the body is executed. The moment you return out from a function, the function state is toned down. That's it. There's no going back to it. There's no way you can continue into the next line and start executing any statement, isn't it? No, you can't. In this case, you definitely can't, because once you return out from a function, there is no way you can go back and execute this line. So this is an example of an unreachable code, a code that you cannot reach. It's just sitting there and there's no way to run it. But now I'll show you some modification here. When you look at what is testfn, it's a function object. Yeah, it's a function object. And when you call it, you just see the code being executed. And the return value is 100. Maybe if you try to get the return value of this, r is equal to, and if you try to print r, type of r, you can see what you see here. The code got executed and it returned the value 100, which is the return, whatever you want to return. It's an integer, right? Now if I try to modify this code where instead of using return, I'm going to try yield. Now this gets a little interesting. Just observe what happens when I run this. Interesting. The moment is a yield 100 inside my function. When I call that function, I get a generator object. This is a string representation of r, which is supposed to be the return value of testfn. Testfn returns something else. We call this a generator object. It says generator object testfn at so and so location. It's a new kind of an object. You can see it belongs to a class called generator. But you can also closely observe that this print statement is not executed, which means that the function body is not executed. The function body had executed. You have seen the outcome of the print function, isn't it? Last time we saw that. And then it returned out. But now you don't see the message, start of testfn. Now, I'm going to tell you what really happens. So I'll create another program where I'll put a lot of yields inside, and you'll see what really happens. This time I'm going to create testfn, and I'll just say start of testfn, just start of testfn. I'll put a yield 100, print continuing in testfn, or rather I'll say back inside testfn. And now I'll put a yield. Okay, let me just scroll it up. Yield. I'm using multiple yields here. Okay, yield hello, print back again in testfn. This time I'll yield nothing. I'll just say yield, and I don't have to pass an argument. I'm going to show you what are the ways you can use yield. Yield, you can use yield with any expression, and the result of the expression would be yielded. What does that mean? You'll understand in a while now. And then I'm going to use print end of testfn. And that's about it. The function just completes there. The function body is completed there. So you can just see that there are a bunch of yield, print, yield, print, yield, print interleaved, right? Print a message, yield out. I think it's better to layer it like this. Print a message, yield out. Print another message, yield out. Print another message, yield, and so on. If you observe, when you call testfn, when you just simply call this function, you'd expect the function body to be executed normally, but that does not happen at this moment. You just get a generator object. Now, this is what happens when this code is getting compiled. I may not be very accurate at this because I've not really dig down deep into the Python source code to verify it. But if any of you do, just let me know whether I'm on the right, I'm explaining the right thing. But this is the way we can visualize things happening. When this code is getting compiled, during compile time, when it's building this bytecode for this, by translating all these statements to bytecode instructions, the compile time of the parser, when it encounters a yield inside a function body, it creates a wrapper to testfn. It creates a wrapper to it. And what is a wrapper? It creates a proxy wrapper on top of it. So testfn might not be the original function, this function that you're executing. No. It creates something else. And that something else masquerades. It makes us believe that it's testfn. So the testfn, though it looks like it's a function object, yeah, it is a function object like before, but it's not really representing the code of this target function that I created. Python does something else. It created another entity as a proxy function object, making us believe that I am testfn, not this guy, somebody else. Like somebody is proxying me, right? So that's how exactly it is. And when you call this function, it does something more. You start calling the original function at all. It creates a generator object. It creates a generator object. And what exactly is a generator object? A generator is an iterable and an iterator. Both. It's an iterable and an iterator. I had to detour and talk about the iterator protocol this time. In this session, I'm going to cover that. I'll explain how exactly things work, and you'll understand it. Now, when I call testfn, it creates a generator object, which is an iterable, which we get here. And this generator object, being an iterable, has access to the original function that he wrote, this function's bytecode. It knows the instructions. It has access to it. So when you try to call testfn this time, rather than calling the original function, it calls another function, hidden function, let's say, which masquerades this original function. And that function returns a generator, which has access to the original function's code. But this generator just comes up to you and says, yeah, how may I help you? Now, this generator object is an iterable. And all iterable objects, you can use a for loop to walk through them, right? To get each item. Now, here's where I'll have to detour a bit and tell you what exactly is an iterator protocol, how Python deals with it, deals with all the iterables, that is, and how it works as a consistent pattern, a very consistent pattern across all kinds of iterable objects. Normally, I'm gonna revisit this back, but I want to tell you about iterator protocol. Then I come back here, you'll understand it very clearly. Let's consider a list for now. Let's consider another entity which is a tuple at this moment. And then we have a string. And you can have many other collections, but I just gave you 3 examples here. You can iterate over A, B, or C using the same format of your for loop. For example, you could say for V in A, and you could just say print V. I'll use end is equal to space to make sure I can make up for other code parts. Or I can say for V in B, I could use print V, end is equal to space. This print I'm using for adding an extra new line, so things look nicely structured or formatted in the output. Or I could use for V in C, I could say print V end is equal to space, and I could print. You can see that the for loop construct looks exactly alike whether you're iterating over a list or a tuple or a string. You don't have to do any special handling. The for loop does not really care whether there's a list or whether there's a tuple or whether there's a string. It just works consistently amongst all of them. I made a mistake here. I think I had a V here. The hello got printed a couple of times. Sorry. Sometimes I type fast and typos do come in. So you can see this is the outcome, right? So you can see that first time it iterates over the list and is able to print every single item separated by spaces. The end is equal to space does that. Next time it's iterating over the tuple, and you can see every single item of a tuple is printed. And next time it's iterating over a string where every single character is printed. Maybe a list is implemented differently than a tuple. A string is implemented differently than a tuple or list. Or you could also I would have used a set, which could be completely different than all of these. These are all sequences. Set is not a sequence, right? It's a different type on its own, different category of type. I could also use a dictionary. So how does a for loop try to manage all of these different kinds of iterables without having to worry about the nuances on how they are storing data or how to access them? So this is what the for loop actually does. I'm going to take a consideration of a list this time. And the moment I write this code, this code that is there here, this code, right? This code, when I say for V in A and say for print V and end is equal to space, this construct, let me tell you what it does. The first thing it does is, assuming that there is A, this A is already defined in here, it calls iter of A. Iter is a built-in function. And this function will try to extract the iterator from a given iterable as its argument. So when I type iter of A, you get a list iterator. Oh, by the way, I created the tuple and a string in the earlier cells here, right? Let me just put them together. So I think you will see exactly what I am hinting at. So let me just try to. I'll also add some more collections. Let's say D is equal to, this time I'll add a set here. And I'll also add a dictionary. I'll throw in a dictionary here. Dictionaries are just key value pairs. This time I'm going to keep it extremely simple. This is a dictionary. Maybe you can also have a range object. I'll just type range of 10, 20, 2 or something. All of these are iterables and all of these are collections. Though the first 3 collections the first 3 and the range falls in sequence, you can see there's a set and there's also a mapping. So all these kinds of collections exist. Now I'm just going to print the result of iter of A, iter of B, iter of C, iter of D, and iter of E and iter of f. All the 6 items I've created, all the 6 objects, I'm calling iter on each one of them. And of course, I will separate the outputs of each of these expressions using a new line. So it makes it more readable. You can see the result of it. A list object has a list iterator. A tuple object has a tuple iterator. A string object has a string ASCII iterator. Oh yeah, remember I used to see that as string iterator, but now I think there's some changes. I need to know which version of Python this change occurred. Maybe it's 3.10, perhaps, or 3.11. I'm not sure. I'm using 3.11, by the way. Earlier, I used to see this in 3.9 and below as str underscore iterator. So names have changed, but it's all the same. Then you have set iterator. For a dictionary, you get a dictionary key iterator, which means you can iterate over the keys of a dictionary. That's what you do, right? When you use a dictionary in a for loop. And for even range, you get a range iterator. You can see that. So different kinds of iterators are returned. So every iterable object has its own iterator. It's like you walk into a phone store to buy a phone. There are people who are specialized in getting you phones. They're the iterators. They'll get you one phone at a time. You walk to a jewelry shop and you start looking for all the jewelries. There are specialized people who know how to get jewelries for you. If you go walking to a book library, you'll have a librarian who will get you what book you need based on how you query them. So the point is that every collection would have their own iterators that know how to get items on your behalf. And this is what is going to interact. Now let's consider back a list here. This list. Let me put it back here. When I call iter of A, as you know, you can get a tuple iterator, which I will store it as iterator this time. Iterator is equal to iter of A. And I'll try to print it out. You can see it shows up as, a list iterator. It's a list, right? I made a mistake. List iterator. The next cell, all iterators understand a function called next. Next is a built-in function again. It's meant to be invoked on iterators. By the way, you might ask me what happens if I call iter of number, any integer. I'll show you that. You say iter of, let's say n is equal to 10 and say iter of n. What do you think you get? You get a type error. You see that? Int object is not iterable because this iter function just queries this target object, says, give me your iterator by using a dunder method, by the way. And this object does not have an iterator available. It says, I don't have one. And then this raises an exception. Duck typing for you. This is duck typing. You don't really, this iter does not go and check what's the type of the object being passed. It's not like that. When you pass an object, it's just going to blindly ask the object, give me your iterator. And there's some objects will return the iterator. Some objects refuse. They say, no, I don't have an iterator. And when they do that, this will raise an exception, telling that, oh, this guy is not an iterable. Right? So that's how it is. The int object is not iterable in this case. But assuming an iterator is returned, that iterator object would always respond to next function. All iterators respond to next. So if at all I try to call next on some non-iterators, like say if I call next of n, you'll still get an error. See? It says int object is not a iterator. You can see that. It says it's not an iterator. However, here in this case, I call next of iterator here. Iterator is a variable that holds the return value of iter, right? So I'm trying to get that. And say next of iterator. What happens? It gets 11. When you call next, remember, there's next, so some of you say, is that previous? No. Iterators go in one direction. Next, 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 next. There's no previous. It's not a cursor. There's a difference between a cursor and an iterator. A cursor has a vector-like position. That means you can go backwards or forwards. You deal with cursors when you work with databases. You get a cursor and you can go one forward or one backward, right? You can do that backward forward motion. But with iterators, it's like you have a box and you say, get me next element, next element, next element, next element. You don't really care about the order. Just one element at a time. That's it. Because think about a set. There's no previous and next type. Set is on order. One item at a time. I throw at you when you ask me, get me the next item. That's it. You can't say get me the previous item because I just threw an item at you. You consumed it. There's no way to go back. Right? I'm producing item one at a time when you ask for it. That's what iterators are. They're not cursors. Okay? So there's no previous and so on. That's a very common question that beginners might have. So I'm just telling you that. So you only have next function to get one item at a time. You iterate over one item at a time. So when I call next of iterator, the first time he's going to get the first one of the items. In this case, the list is ordered, so it gets the first item that it can, which is 0th item. Again, when you rerun this cell and say next of iterator, you get 22. Next of iterator, 33. Next of iterator, 44. Next of iterator, 55. Now we can see that we're hit to the last item of this collection. If you call next of iterator after this, you get an exception. And a special exception is called stop iteration. This is a way of the iterator just like you. It's done. There's no more items. It's empty, right? And that's exactly what happened here. Now, understanding this logic, this is how a for loop is actually doing its job under the hood on our behalf. So when you actually type for V in A and you're trying to process something in here in this body, this is what the for loop does. I'm going to put a cell below here so you can see the for loop on top and you can see what happens below. The other cells are for your learning and experimentation at the low level, right? So create a cell here. So assuming that you have a list like this, when you type for V in A, what really happens is first it extracts iterator. The for construct in Python extracts iterator by calling iterator is equal to iter of whatever the target, it's A. And then it uses try block. I'm using try except for no time. Okay, this time I'm showing you a little more elaborate. Try block. Inside a try block, returning while true. Yeah, there could be a lot of optimizations in real world. This is just a very layman's understanding about the most generic implementation, what I'm showing you. But then there are a lot of optimizations under the belt in Python. So when it comes to handling how different kinds of iterables are handled, right? I'm not going to that implementation aspect as of now. It's just our high level understanding in this case. So it's like running a while true. What does while true mean? Infinite loop. Infinite loop. Forever. You want to say while true? I would just type V is equal to next of iterator. And that's the V part in the for loop. Whatever you put here, whatever variable you have here, that variable is here, right? The variable is initialized by calling next of iterator. So what does it do? The iterator will get the next item, and that item is assigned to V. And now the for loop body is executed. The code that is in the for loop body, that gets executed, which in here is like print of V end is equal to space. And this keeps going on. Eventually, when next raises an exception, which is stop iteration, that will be gracefully handled outside like this. Stop iteration. Silently come out. Now see this. When I run this code, I don't need this extra print anymore because I don't have any other code here below. So it's only this for loop, right? Now run this code. What outcome you get here? I get the same outcome when I run this one. You can, in a way, think of the for loop implementing this kind of logic under its hood. So when you say for item in iterable, the for loop will basically find out what iterable you pass there. It's going to call iter of that iterable and get the iterator. And then it's going to run a loop internally where it's going to keep calling next of iterator. What is returned, the for loop body will use that with that item is equal to next of iterator. And then once the body is completed, again it'll call next of iterator. Keeps going on forever until the next raises an exception. And that exception is more specifically stop iteration, because I'm only interested in the stop iteration. If any other exception is thrown, you want to pass it on to the caller, but this exception, I gracefully hand load because the moment this raises an exception, the control gets out of the while loop and the try except just handles that exception gracefully and it just comes out. And you wonder why this pass is required because, this is a compound statement block. You want to say do nothing, just come out silently. That's why I'm putting a pass here. And this is an equivalent of what a for loop does. And this, what I tell you, is the iterator protocol. Now you can substitute a list with anything. Maybe you can substitute this list instead of a is equal to this. I'm just going to comment this off and say a is equal to hello. And still this same algorithm works fine. You can make it a dictionary. You make it a set. It works. Because this code is very generic. You pass on any argument to the for loop in here, right? Whatever you pass here. All it's going to do is it's going to call iter of a. If that responds with an iterator, it continues. If it raises an exception called, type error in this case, let's assume if it's not able to return an iterator, you get a type error. It's not going to continue. See what happens when I say for v in instead of a, if I type n here. I think n I created in one of the cell as a number. What do you get here? Int object is not iterable. We saw that when you say iter of n, you got the same error, right? That's what happened in the for loop. It calls iter. Once it returns an iterator, it starts calling next on it until the next raises an exception called stop iteration. So with that being said, now you understand the iterator protocol. When you learn classes and objects in Python, and you learn about object-oriented programming, which I will not do in this series, but another series, another set of tutorial where I purely focus on Python object-oriented programming. I'll title it accordingly, right? And there I will tell you how you can implement your own class, your own object, which conforms to the iterator protocol. These are called as iterable objects, custom iterable objects. How do you create them? Using classes. But you can get away with generators, which I'll show you now. Now, retracting back, all the way back. Remember I talked about the testfn function? And I told you that when I call testfn, in this case, because there's a yield statement inside it, this function when you invoke, returns a generator. Because it's not calling the original function, Python might have created another proxy function masquerading this, and that is called instead, and returns a generator. And the generator that's returned, the generator object, that particular object is an iterable object. What I mean by saying that is, if you take this G, I'm going to put it in the next cell now here. I type next, I'll say iter of G. This is a special case. Normally, when you call iter of a list is the iterable. When you call iter of it, you get another object called list iterator. When you call iter of string, you get a string iterator. So you have an iterable and you have an iterator. But here, when you call iter of G, it says, I'm the iterable and I'm also the iterator. So generator implements both the iterable and iterator features. So now when I call iter of G, we can see that it just returns a generator object itself. It returns itself. You can see the same object is returned back, which means that whatever is returned by iter, you can invoke next on it. The moment you say next of G, just observe what happens now. Start of testfn, and then the return value of it is 100. You know what really happened? The moment I call next of G, next on a generator object, this is what kickstarts the generator by executing the code of the original function. Whatever code you wrote in the function, that function code is executed, but it does not run to completion. The moment it sees a yield and whatever value yielded, it returns out that. The return value of the generator is, the generator will think of the generator enters this code, executes this function, returns out what do you yield here. In a very and the analogous way of the other analog I can talk about is like similar features. Like if you ever use with debuggers, you put a breakpoint in a line, you execute till that breakpoint and it stops right there, and you can see what's the value, right? Something like that. It's like it is not tearing down this code. It's having that code in place. It's executing line by line of statements or statement by statement in this code until a yield is encountered. The moment the yield is encountered, it gives you back the control, but that code is not turned down. It's still maintained. The code is still maintained. And now you got this as the return value. What you yield is return value. Again, when you call next of G, what happens? It continues back where it left off. See this. Back inside test event. What is happening here? Is going back into this code, executing this statement. And the moment there's another yield, I said yield hello, that becomes return value. That becomes return value. In this case. Again, when you try to run this, next of G, it goes back again inside testfn. And this time I'm coming out by using yield. But this time I'm not yielding out anything. So this next does not return any value. You can see that this print is from the function body, but next return value is empty, right? It's none. When I call next of G, and now you can see it raises stop iteration. Why? Because the target function ended after printing this message end of test FM. And that's what happened in this case. So you can see this generator implements iterator protocol. So you transformed your function into a generator by using yield here. The moment you use yield, now you can use this function in a for loop, this code, and get to execute chunk of statements, statement to statement. So if I want to run this again, I'll just copy this cell again one more time. Here, I'll just copy this, paste it all the way down here, all the way down. I'll paste it here. And then this place, I pasted it. Yeah, I pasted it here. This time what I can do is I can just type for v in testfn. I can just type here in for loop v equals v. That's it. All right. Let's see what happens when I run this code. You can see how the statements sort of interleaves execution. You can actually see that the moment I say for v in testfn, the for loop would have called iter of testfn, whatever testfn returned is a generator, because I'm calling testfn, return value of a testfn generator. The for would have called iter of that generator object, and on that generator object, it will invoke next also. The moment it invokes next, you can see this code gets to execute, and what is yielded by the generator is assigned to v. That's return value of the generator's next function, right? The next function, return value is assigned to v, and you can see the for loop executes now. A statement in the for loop got executed. That's what this is, right? So you can see the for loop executes. Then control goes back to this testfn to execute a statement. And because it yielded out hello, now control comes back to the for loop statement, executes this. Again, the control goes back inside this. Again, the control comes back into the for loop. Again, the control goes back into this. And after this, because this generator completes, because the code completes, it raises an exception, which is stop iteration, and the for loop silently comes out. It's a kind of doing multitasking. Do you see that? So you have two kinds of things happening. You execute some statement in the for loop, execute some statement in this function. It's code, right? We call this a generator now. Calling a function is a bad idea because functions are run to completion entities. Though use def keyword to seemingly define a function, the moment you put yield statement inside that, you cannot call that a function anymore. It's a generator. That's it. You call it a generator. The moment you have yield inside a function. So this generator code gets executed. Control comes back to the for loop to run something. Again, you go back to generator. You're shuffling tasks. Multitasking, right? And this is an example of concurrent execution. And now, with all this being said, when you go and check what really happens in this Fibonacci generator that I showed you, it will all make sense now. Now here, look at this. I say R is equal to fib of 10. What is R? It's a generator object because there's a yield inside fib. It doesn't matter where you put it, inside a for loop, inside if condition. The moment there's a yield statement inside a function body, Python transforms that to a generator. So calling fib will not execute the function body, will return the generator object. So whenever you have yield statement, calling such a function which has got yield inside it will not execute the function body immediately. It rather returns a generator. You have to iterate over the generator in order to get the body of this function to be executed. That is a very important thing to note, right? So you can see that when I say r is equal to fib of 10, then a generator is returned. The moment I say for v in r, this is where the code begins to execute. This code is executed, it goes inside the for loop, but now it yields out a. What is the value of a this time? 0. You get it as v. And now we print 0, 0 into 0. And now when you say next of this particular generator, r, now what happens? It continues to this statement where it puts a block sleep for 1 second, wakes up after 1 second, then you can see it shuffles its numbers and next value of a is generated. And then you can see that it goes back here and says yield a, and the control comes back into the for loop body, printing that as v. So control switches between the fib and the for loop, and this code is now running concurrent. So as and when the fib is throwing numbers at you, you process in the for loop on the fly, so you don't have to wait for the entire list to be created and given to you. So you're saving memory. You're not creating a list. So it's saving a lot of memory. And this code, this for loop, does not have to wait for this entire fib to complete its job before proceeding. It can work simultaneously, or let's say concurrently, along with the fib generator. So this is an example of how generators work. Now in this session, I just gave you an overview of what a generator is and how you can create one, what exactly happens when you use yield statement inside a function, how it transforms to a generator, and I also talked about the iterator protocol and how a generator implements the iterator protocol, how it is an iterable iterator object, and therefore how you can use them in a for loop. So I told you how you can transform function to generator and make it concurrent. So it runs with concurrent code. In the next session, I will give you more use case examples and patterns in using generators, right? How generators work. And I'll also tell you some not very commonly used features today where you can use yield expressions, which is a generator is a producer. It produces values. You can also build a consumer part of it where it consumes values, accumulates values. I will show you an example for that using yield expressions. But these are not very commonly used today, but you can use them. And then if time permits, I will introduce you to what we call as coroutines, the official coroutines that made its way starting from Python 3.4, but it's like refined over time. By the time Python 3.6, I guess 3.7 is released, they sort of ironed things out and is now used in the mainstream with the async def keyword and how you can use some kind of multitasking. What are the different kinds of multitasking patterns these coroutines and generators are applicable for? I'm going to be covering that in the next session. So I hope you understood what generators are, how you can write a generator in a very basic way, and how they work with this example, right? With all the examples I showed you. If you have any further questions to it, you can post them on comments, but look into these examples which I gave you. Try it out on your own. You'll start connecting the dots. As I told you, you just watch this entire video and just listen to it. It'll all go in the air until you try it out, explore, experiment, and then you start connecting the dots and you'll see exactly how they actually work together, right? So if you have any questions, do post them in comments. And as usual, if you like this video, this kind of information which I'm putting forth, please hit the like button and do subscribe, and you will get more videos like this posted in your notifications. And I'll see you in the next one. Thank you very much.